So as you can see, this was a sketch that I gave you last week in the questions. And the question was to compare the advantages and disadvantages of the two constructions there, one heavy, one light, and to discuss the advantages and disadvantages in terms of insulation response times, cost, and performance. Okay. So what we can see here then, we can see clearly, let me just get the highlighter. We can see here that obviously this is 200 mil thick, as we can see there. In fact, let me just get rid of that highlighter there, we won't need that. So we can see 200 mil solid concrete, and it has a value, a U value of 0.1 meters squared Kelvin. And then on the other side we have an insulated board which is just 50 mil thick, so 4 times thinner than the concrete, but this too has 0.1 watts per meter squared Kelvin. So in terms of performance, they both perform the same in terms of the heat lost through the wall, of which both conform to building regulations. Remember, building regs was 0.33, or sorry, well, 0.3 watts meter squared Kelvin. It's actually 0.33, but we'll round it up. So in terms of insulation response times, the heavy construction, in terms of high thermal, let's say this is, let's choose a pen here. So we've got here a high thermal capacity, and on this side we've got a low thermal capacity. So what's the difference between the two then? Oh, of course, one's high, one's low, but what does that mean in terms of design in construction? Well, we need to go back to previous sessions where we covered thermal mass, which is about the way that solid objects, solid molecular structure materials such as concrete, absorbs energy in the form of heat and stores it and releases it over a long period of time. So this is where the advantage of heavy construction and high thermal capacity works, is that obviously the sun's going to beat down all day, or heat is going to be transferred into the concrete itself, and at night time it's going to slowly release that energy, so it's going to cool down. It's going to take a lot longer to cool down, but likewise it takes a lot longer to heat up. Whereas the low thermal capacity, although it has the same U value, 0.1, it rapidly heats up. So we're talking internal walls, bedrooms, living rooms, where we put the heating on, and we want rooms to heat up very quickly, and also that the heat's going to transfer through both sides. So you may have a living room on the right hand side of that of this wall here, living room on the right hand side, and you might have a dining room on the second side. Well, the two rooms are going to heat up fairly quickly, even though the insulation value is the same for both examples. Obviously, for domestic internal construction, we want a fast heating inside the room. So there's advantages and disadvantages. That the heavy construction has an advantage where it will release energy over a lot longer period of time. The disadvantage is it will take a lot longer to heat up. And then the light construction, very quick to heat up the room, but it doesn't hold the heat as long. So therefore, when you turn the heating off, the room is going to cool a lot quicker. Now, if we move on to cost, there's an advantage and disadvantage there, obviously. So on the concrete side, we've got 4 times the thickness. So we've got the cost of concrete, which is, let's put this over here, cost of concrete. Prices do vary, is approximately £110 plus the dreaded VAT per cubic meter. So you would simply work out obviously the size of the wall, the length of the wall, and then the depth, the thickness, the width, the height, so on and so forth, to work out how many cubic meters of concrete. And then of course you can either buy these prefabricated so that the wall slabs arrive already made up for you, which would be more expensive, or you could pour it in situ, which you would need a formwork system to hold the concrete in. Like formwork system is like a mold, a big massive mold where you pour the concrete in and then you strike the mold off. In other words, after a couple of days, when the concrete is curing, the molds are pulled away. So you can say that that's going to be very costly. In terms of advantages of maintenance, there's very little maintenance involved. With concrete wall, it is over a longer period of time in terms of acid rain if it's exposed to the elements outside. On the inside, no maintenance at all really. On the light construction side, we've got insulated board, 50mm insulated board, and one sheet of insulated board. Now these vary greatly. There's so many different types, thicknesses, makes. You can have foil backed, you can have moisture backed, you can have a 25mm. Effectively what you've got is, let's see if I can draw this. You've got plasterboard here, and then you've got a thick skin of what looks like foam, solid foam, that's glued to the board, etc., like that, and then the whole thing as that is fixed through the plasterboard into a stud or into brickwork, so on and so forth. So that's what the light construction, the insulated board, would look like. And one sheet of insulated board, the approximate cost, oh, give me a pen, that's still not worked, there we go, approximately £60, and that would be 2.4 meters by 1.2 meters. And as I said, it'll be a dry fix very quickly. Labour cost very low in comparison to the heavy construction. So overall, they both have their advantages and disadvantages, as I've pointed out. If you have 70% understanding of what I've explained now, it indicates that you're researching well, that you're understanding the subject better. Hopefully this recap here has filled in any gaps in knowledge for you and just gives you a few ideas in how to think in different ways with regards to making justifications and evaluations in terms of materials or performance or cost, in terms of when you're faced with a number of possible outcomes for a client. So you just need to get into the habit of looking at different aspects in terms of performance, in terms of cost, in terms of ease of installation, in terms of labour, in terms of, lifting equipment, machinery, so on and so forth. So okay, so without further ado, we're going to close this off, and then we're going to get on with continue with this session for heat loss and heat gain. Okay. Okay, so heat gain and heat loss, a sustainable view. I mean, we've covered heat gain, heat loss in various explanations about U value, fabric heat loss. We've spoken about the temperature to air differences between internal and external, so on and so forth. And I think the obvious is about proper design, sustainable design, the correct or the appropriate selection of materials that are going to perform in use and that they're going to be advantageous to us. But the problem, and I think we all know where we're going with this, is climate change, and it's having a massive effect on construction, simply because of the effects, local and global climatic effects on structures. This was an interesting extract that I found on the internet. In 2010, the world's buildings accounted for 32% of global final energy use and 19% of energy-related greenhouse gas emissions. So a little bit later on in the course, we'll start looking at sustainability in more depth. And what we have to understand is that we don't just produce materials for a building and then just count the CO2 that's involved, or the carbon monoxide, carbon dioxide, all the usual suspects of greenhouse gases and carbon emissions. That happens when we extract the raw materials. It happens when we produce the materials. In some materials, extremely high temperatures like concrete, Portland cement is 1,500 degrees. I mean, how much coal are we going to keep throwing at that? Because we still use coal for that. We do use renewable energies, but generally we're not going in a very good direction at the moment. So we talk about what we call the embedded carbon energy with building structures, and the emissions in the tangible construction, and also for the whole life cycle of the building, which is generally 65-70 years. So that building will produce X amount of carbon emissions, of which is going to contribute to climate change. So the use of energy in buildings globally could double or even triple by 2050. And the drivers, what they mean by the drivers is the factors that is driving that forward towards that unbelievable figure, is that billions of people acquiring adequate housing and access to electricity. So as we evolve across continents, there's some major third world countries coming up on the rails now, where they're extracting valuable resources from the precious metals and stones from the ground. They're exchanging that for infrastructure. They're building skyscrapers from literally off-the-shelf plans from the Western world. But the problem is that the Western world made a lot of mistakes in terms of heat loss, heat gain, not really keeping their eye on the ball with carbon emissions. And so these plans that exist, that we've built from and tried to learn from, they're actually being replicated now in the third world. So that the problem is just coming back at us, and it's just going to keep contributing. So another quote was, widespread implementation of best practices and technologies could see energy use in buildings stabilise or even fall by 2050. Okay, so, and they say many mitigation options promise multiple co-benefits. To give that some explanation, the mitigation for the options is all the different reasons why you would use all these various options, because they are going to give you so much benefit going forward. Okay, so effectively that's what it means. But what they're saying is that we really got to take or seize the opportunity and move forward and design buildings in a better way. And heat loss and heat gain is incredibly crucial for human comfort, the running of the building, the carbon emissions that's involved, and we've really got to try and find a better way of doing things. So the impact of local and global climatic conditions on our structures is what we're going to look at, and I say in a sustainable sense. We look at certain things. I mean, if we take structures in the UK, for instance, we've got extreme heat conditions. We're experiencing 35, 38 degrees in the UK now. That's extremely unusual, and it's getting more and more usual, so to speak. We can expect the same temperatures next year. We can expect crazy temperatures in November, t-shirt weather, and then we can get snow in April or May. So things are really, really impacted heavily. We a couple of seasons ago, I'm talking about football now. A few years ago, we had such an extreme winter. I mean, it was down to minus 15, minus 18 degrees in this country, which is just insanely cold. That is ridiculous. So, some countries, they're minus 40, minus 50 degrees, and I wouldn't want to be living in a climate like that, but they deal with it. But things are changing for them as well. So we've got to look at things like, I mean, we mentioned before, when I talk about the cricket with the biomimicry, with the cricket cut in half, and that they cool themselves down by passive ventilation, so just wind or just air circulating through the body to cool it down. And I spoke about buildings, and I'll bring it up again a little bit later on in this presentation about that passive ventilation. We got to talk about, do you remember the stack effect when we had the building with let's just have a quick, so let's build. So here's the building, if you remember. Fine building it is too. And if you remember, we had a neutral line through the house there, of where, when we talk about the balance or the stack effect that we had this cold, cool air being drawn in from the bottom through gaps in windows and doors in fireplaces, so on and so forth. And then that was ultimately, it went out in various directions through the top of the house, through the roof, and this was called the stack effect. And we talked about balance, didn't we? We talked about equilibrium. Okay, let's just get that in there, equilibrium. And it was about the pressure. It was all about pressures and the cool. And if we move the zero axis, that central line through the house, if that was to rise up, then we're going to have a problem with too cold. And if it lowers, if we have not enough cool air coming in, we get a build up of heat, then that's going to affect our human comfort. So we need to stay on top of that. Things such as flooding is getting more and more common now. That has effects on foundations. It can raise an already high water table when we start to get water ingress, rising damp, infrastructural damage, which is detrimental to the structure itself. These are all things that, that they're major headaches for designers, and you will be part of these designs going forward in the future. So one of the things that's key in design is about materials. Okay, so getting the right balance of materials, the materials that perform. They give the U value, they give a high thermal mass, they give a low thermal mass depending on where we want it, the design of the building. So we've got to take advantage of what we know now, and we've got to produce structures with the cutting edge options available to us. So we talk about those mitigating options that has code benefits for all. So we can see here sun shading devices allow winter to enter the building while shading during the summer. So who doesn't like a bit of winter sun? But obviously when you're getting winter sun coming in, you don't need to turn the heating on as much, or it's going to warm up. It's going to warm certain elements of thermal mass around the structure. Solar panels will obviously gather energy to offset electrical costs, so that's a big plus. We've got the operable vents in skylight, which will help cool the house. So we're going to talk a little bit more about how to ventilate, how to cool the building down. We've got number 4 there. We've got vertical circulation, creates a light well, allowing daylight into the interior. If anyone's been to Coventry University, the library, that was designed by the students, and they've got the light tunnels on top of the building, and the what they call the exhaust vents, big. They actually look aesthetically quite nice, but it's a very, very well designed building, sustainably cutting edge at the time. I can't remember the name of the building, not the Windsor. It might come to me. But however, that's a really good research point to start with. If you look at the Coventry, Lancaster building it's called. Yeah, the Lancaster building at Coventry University. You need to look at that if you want to look at how to light and cool the building, to heat a building and cool the building. It's absolutely brilliant. So heat gain, heat loss really does start there. Lancaster building. We've got strategic window placement, and that will enhance natural ventilation to help cool the building, because don't forget, cooling a building is incredibly expensive. I mean, it's not the cheapest thing to heat one, But at the end of the day, if you build a house with lots and lots of windows and glass, etc., you're going to have a big problem with cooling it down because of the solar gain, unless you put expensive argon gases and so on and so forth in the double or triple glazing to try and offset some of the heat coming through. We've got the insulation, rigid insulation with an air gap to create that flow, that passive flow. Shipping containers are reused resource, making them highly sustainable. So you can see from this picture here that it looks a lot like that's a half a dozen shipping containers. I've actually seen this on Grand Designs, where a few examples of that show where somebody's used the shipping containers, and you wouldn't know. It's just absolutely stunning what they do with them, but they just generally left to rust into the natural surroundings and become a bit of an eyesore. So why not use them? And super efficient radiant floor heating systems. I mean, there's lots of different heating systems, and a simple thermal mass heating system is a concrete floor. Believe it or not, concrete can be polished up with beautiful staining effects to make it look like marble. Very expensive, but still a solution because it absorbs heat and emits it over a slow period of time. So, as I mentioned, let us not forget biomimicry. So this is about where we're mimicking nature. So what animals do, and what plants do, and anything around us that we can observe and learn from. And these metallic strips, if you remember, effective what you can see here is in slide number 1. You see a certain type of metal with a certain thickness, and when you deliver heat to it, energy, you can start see all the way through to number 4. It curls right open, and if we was to place 1, 2, 3 pieces of that material together, bond them together, we can change the thicknesses of those materials and make them ope or curl at certain temperature, which leads us to this, which is the biomimicry. This was Dr. Kim Sung. I believe she was Korean, or is Korean. I'm not talking her in the past sense. But you can see the way, let me get a coloured pen here that will, so I don't clash with, let's try this colour here. So you can see in this example here that it's 60 degrees Fahrenheit. If you want to convert Fahrenheit, it's times 0.18, times 1.8 plus 32. So that'll give you an idea of multiply. So yeah, 1.8 plus 32 will convert centigrade into Fahrenheit. So you can see here that the wind at the moment is hitting the structure and it's being rebounded off. Okay, like that, because at that time the building is not designed to open at 60 degrees. However, now you can see it's reached 80 degrees and now they've started to open up. You can see that the system here, you can see that there where they've curled open, as opposed to on the other side, on the left hand side, where they're absolutely flat and straight. But you can see here that they're all opening up here and creating those gaps, those vents right through to the other side. Look, you can see them there, just there, look, and you can see that the air is now traveling through, which is obviously cooling down in between the floors like that. So it's free ventilation is the way you want to look at it. But that's what we call passive ventilation. That's about controlling the heat loss in a building and cooling it down. So, and what happened there is once it's got to 80 degrees Fahrenheit and it's all opened up, it'll drop back down to a certain point, or it'll maintain at 80. If it opens up at 80 and then it goes to 100 degrees, well, largely this will keep the building cooled to a certain point where you may have to have mechanical ventilation kick in at, say, 90 degrees because there's not enough airflow going through. But it's not a one-size-fits-all answer, but it certainly is a huge contributor to bringing down costs of ventilation and air conditioning with refrigerants and so on and so forth. And so on to the passive house, what we can see here. Let me just draw that there, passive house, and I believe that's German. And effectively what this is a it's a standard of construction that is incredibly sustainably efficient, and it's possible that you can go on the website and you can complete. There's actually a planning process. Or what I mean by planning, there's an actual template of what you can put information in, or you can see examples of it, and it's called a PHPP. I suppose that's passive house preparation plan or something like that. But it'll assist you or people wanting to construct houses and homes and structures, etc., etc., to be more efficient. I mean, if you look at number one, it uses 90% less energy to heat than an average home, and the heating costs around £75 a year. Now, if you go to your parents this evening or tomorrow, you remember to ask, or if you're the bill payer in your house, you'll know that £75 a year for energy that's a monthly payment in the homes that we live in. That's crazy. That's 1/12 of it. There's lots of other, your mechanical ventilation with heat recovery, your MVHR, and which is a brilliant piece of kit. That's it looks like an air conditioning unit on the back of your house, and it works like a refrigerator. With it's to do with compressing gases, so on and so forth, which is exactly what your refrigerator does to extract heat. But this is the other way around. It extracts the energy from the air. And it can, for every 1 kilowatt of energy that you put in, so 1 kilowatt, a 1 kilowatt hour for electric is around 13.5 pence. 15.5 pence. That's at my house. But it returns 3 kilowatts of energy. So for every 1 kilowatt hour you put in, you get 3 out. And this is the stunning thing about this, is that it can actually recover heat from air that is minus 15 degrees. That is absolutely stunning, and you can get these retrofitted in your houses, and new builds going forward will be built with these in mind, because I believe it's 2023, no new built houses can have gas installations anymore, so no more gas boilers, no more gas cookers, so on and so forth. So this is the way forward. So these are the kind of things. Super insulation. This is a really good slide to look at and to think about things in terms of heat loss and heat gain, and especially with the big sustainable message that I'm trying to put across. That's the end of the session. Don't forget to complete the question, of which will be attached to this, and just to finish off by, what I'm going to say right now. Answer the question and give the question back.